Someone recently sent a link to one of these power plugs on eBay, and this is one of these power analyzers that you plug into a socket, you plug your appliance into it, and it monitors how much power it takes. It records peak power, and it records the overall consumption during, say, a day or a multiple of days or whatever you want. And you can actually program the cost into it by, if I reset this to scratch, you can program the cost in by holding the cost button for a few seconds, and that starts flashing. You press function to step through digits, and in this case the local power cost is 17 pence a unit. So you can scroll along to put that in and then press cost again, and it will give you an actual cost of the running costs of your appliance. It's a very useful device. So I had one of these in the house, but I have tidied up recently and couldn't find it. So I thought, well, what the heck? Let's buy another one and we'll test it. And I have to say, I've been comparing this to the Hopi. And it's got one disadvantage in the sense that it only displays one parameter at a time. You know, it will display watts, then it will display the units used, then it will display voltage, and then current and power factor. Whereas the Hopi displays them all the time. However, the accuracy is really surprising. I tested this at various loads. I tested it with a 1/2 watt LED lamp, which is quite an awkward load, and they were pretty much identical. There's a slight decimal point difference between them, but that's it. As the power went up to 100 watts, this one drifted by about 1 watt, and other things, like I used the Fluke to test the voltage reading, and it was at 240 volts, it was only 1 volt off, so it's actually really surprisingly good. One of the things I tried, a couple of things I tried, I thought let's test it with a really low load. So I tried the Hopi with just a couple of resistors, 120 ohm, 120k resistors. Well, that's where I did make a mistake. I did actually, you'll see these little black crispy resistors. I did actually put two 120 ohm resistors in series to make 240 ohms instead of 240k. And at the point I saw the smoke coming off them, I realized I was looking at them going, oh no, and then they exploded and the power went out. Right, anyway. Once I'd restored normal vision and reset the breaker, I stuck these in, and it wouldn't read them, it was too low, but the Hopi wouldn't read it either. But there is an interesting thing. If I bring up my quick test, the quick test, I've actually got just a capacitor stuffed in it, because one of the things that's slightly annoying about the Hopi is that it doesn't tell you what it doesn't show a very poor power factor load. So for instance, some of the LED lamps that are rated 1/2 watt just won't show up in the Hopi, and I'll show you that. So I'll plug this in, and this is actually passing current, but it's because the power factor is so bad the Hopi just ignores it completely. It might just be stabilization at lower levels. If I just plug this in here for the convenience, I plug it into this socket and I plug this in, then this displays about 37 milliamps with an absolutely shocking power factor, which is absolutely spot on. Now I'm going to unplug this, take the capacitor out. Yeah, that's got a charge in it. I shall remove the capacitor. I shall find a metal object, like a pair of pliers or snips, and just a slight crack, nothing really major. Sometimes it depends when you disconnect it in the sine wave, it can hold quite a crack. So far I am really impressed in this. You know, it is seemingly very accurate. So let's open it up and see what makes it tick inside. Oh, there is one other thing I noticed. I was trying every button combination to see, this is a battery in it, by the way. When you press this button, it wakes it up. I tried every button combination to see if I could put it into calibration mode. And I found one mode that might be calibration mode. I'm guessing it'll be software calibration. It's how they normally do it. If you press down, and I'll hold this at an angle, and you reset it, and then you hold the button and it goes 0419, could that be the month and year it was made? 2019, not really sure. But then when you release it, it displays 3, 2, 1, and then 0. And I don't know, maybe there's some calibration procedure. I don't know if there's trimmers inside, or if you just plug it into a known voltage and a known load current, and it calibrates off that. But anyway, I digress. What I want to know is, what's inside? So let's whip the cover off this. It seems to be held on by 4 screws. This is a universal unit. You'll see that, in fact, I wonder if this screw here just holds the plug on. I shall find out. I'll test that, see if it opens. It takes different types of plugs and sockets. You know, it's just a little round insert. Let's try it and see if it... Oh, it does actually come apart. Okay, so that screw there doesn't have to come out. That just holds this in place. What do we have? We have a very sparse circuit board in here. Let me zoom down in this. That's very bare. There must be a lot of stuff on the other side, unless all the processing is being done in here. Let's whip that out, that board, and see if there's anything in the bottom of it. I see a crystal, so there must be stuff in the bottom of it. I would expect that. Power analysis would be done in the vicinity of the... Oh, there it is, in fact. Now, is that either a processor or is that a dedicated metering chip? There's the shunt wire there that it measures. If you see this big shunt wire, that's all the current to the load flows through that, and it measures the voltage across that to determine the current that's flowing through it. It's amazing that it can be as accurate as just a few milliamps for such a solid shunt, just like in a standard test meter. I'm seeing a string of resistors here, which might be part of the sensing. I'm guessing this might be a dedicated chip, because I don't think a microcontroller, unless it's a dedicated power analysis microcontroller, could actually do that. We'll find out. I'll take the rest of it apart. Oh, I'll tell you what, let's take a number off that, if I can. V8261F? Or is that 251F? Not really sure. It's quite hard to tell. But that's okay, I can look at it afterwards. What's the little other chip? It's a 78L05. That's probably a Zener Diode as part of this power supply circuitry. Let's take the front panel off. I hate these little ribbon cables. They are so much trouble. They've put hot melt glue in that to try and keep it from breaking, but it's not uncommon for those to break. Let's whip all these screws out. What am I expecting on this? A display driver? Maybe just a blob? After I've done this, I shall reverse engineer this. I'll take a picture of that board, and we can analyze it and see what we can find. This is where it will have zebra. Either the display, I don't actually see screws holding the display onto this unless I've already unscrewed it. But I would expect zebra strip onto gold contacts. Maybe. Yeah. Zebra strip is layers of alternate conducting and insulating material, which couples, because the LCD display is very low current, it couples an image of these contacts onto the LCD display. What do we have here? We have magnifying glass, a Holtec HT1621B, and a SC92F7351M. Don't know if you can see that. And the Holtec. The Holtec chip is the one that's going to all the LCD pins. Is that a microcontroller with LCD display driving capability? So what's this then? This one is going to the buttons, so that could be a microcontroller. Tell you what, I'm going to reverse engineer this, and we'll see what's involved in it. So I'll be back in one moment. Well, that actually took longer than expected, but let's start with the spicy bit of the circuitry first. It's the main little processor card in the bottom. Well, I say processor, this isn't a processor, although the data sheet for this is actually about 100 pages. This is a proper power analyzer chip. That explains why it was so accurate in the way it detected the power factor and things like that, and the voltages and currents. So notable things on this board, we've got the capacitive dropper capacitor, which is over here. We've got a series resistor, quite a high value, a power one, 100 ohm, purely as protection against sort of inrush current to the circuitry. We've got the nickel metal hydride backup battery. That's 3 little button cells together giving 3.6 volts. We've got a crystal for this chip here. And we've got a big, heavy, high current shunt. And that chip, that's across these connections here, and the chip is actually measuring the voltage across that to determine how much current is going through the load. Things worthy of note before I bring on the schematic. Things worthy of note are this chain of resistors here, which are being used to limit the current and form part of a potential divider for measuring the voltage. A couple more resistors here going up to a transistor, which I'll show you in a moment, and 78L05 voltage regulator, some capacitors, Zener Diode, and this really important chip. I shall show you the chip first. Let's tame this down, that is far too ferocious. The chip contains a lot. Seriously, it's a very complex analysis chip, but the main things we're interested in here are these two inputs, which are measuring voltage and current, and then lots of heavy processing and computing, lots of internal voltage references, 1.1888 volt reference, notable, and a 3.3 volt reference, and then loads of processing, and then data, a data network, transmit and receive, that can communicate with the microcontroller on the display panel, and it can actually calibrate, it can send information down to this and program it into its registers when it boots up to actually get this chip pre-calibrated for what it's going to be reading. I guess there must be a calibration mode. I don't see anything on this for adjusting calibration. Let's take a look at the schematic. So this is all the power handling. Let me zoom down just a little bit on that. That was quite a rapid zoom. So if we start at the circuitry, we've got live and neutral coming in. Things that are worth mentioning are live is the base voltage inside the unit. Everything is referenced to live. It's effectively 0 volts, but obviously because it's live, it's in the UK it's 240 volts. It most certainly isn't 0 volts, but all the circuitry sees it as being 0 because it is the base reference. If we cover all this circuitry over here and we look at this bit first, there's a few resistors here forming a potential divider, limiting the current into the base of this transistor. And that means that on every half wave, this transistor is basically, it's on for one half wave and off for the other half wave. And it basically goes, that transistor then just basically goes up to the display card, the LCD display card. It comes up one of these pins and goes to the microcontroller, because this is the little microcontroller that's running the whole show. And that is just an LCD display driver after all. After that, we have what looks like it's starting off as a capacitive dropper. The capacitive dropper has a 470 nanofarad capacitor, which I thought was quite high, given this isn't actually switching relays or anything like that. It's not got any high load. But 470 nano with 2 resistors in series, which is good to spread the voltage for discharging that. So when you unplug it from the wall, you don't get a little tingle off the pins. Then there's the 100 ohm, that high power resistor. And then on each half wave, because you can't take the capacitive dropper and just put it through a bridge rectifier, because one of the supply legs is reference to the 0 volts of the circuitry. So it's basically a half-wave capacitive dropper, but you can't just use a single diode. It still has to see that push-pull to have the capacitive dropper effect, where it lets through a little bit of current in each half-wave. So in one half-wave, it finds an easy circuit through this diode. In the other half-wave, it pumps through this diode, and it charges this capacitor up. There's a 100 ohm resistor, more current limiting to the Zener Diode, which is around about 12 volts. I powered the circuit up, I measured it. It was around about 12 volts. So that gives a 12.9 volt rail. There'll be a little additional drop across this resistor. And that's going up to the display. It's not actually used. It's not used anywhere other than to derive the 5 volt supply from it. But it does go up to this pin on the display card, suggesting there was probably an option to have backlighting But then it goes through a 470 ohm resistor to help dissipate some of the power, and then a standard 78L05 voltage regulator. Was that a 78L05 or a 78M05? A 78L05. It's just a low current 100 milliamp regulator. And then, so that's one big smoothing capacitor, then a smaller smoothing capacitor, and that gives the 5 volt supply. That 5 volt supply goes to the energy calculation unit. This chip runs at 5 volts, but it derives its own lower voltages internally. Quite complex. The 5 volt also charges the nickel metal hydride cells via this diode and via this current limiting resistor. But then it also goes out to the display card and gives it roughly, I measured it, 3.36 volts, with each of these diodes dropping a little bit on the way out. And when the power is turned off completely, then the nickel metal hydride cell will go via this diode, which will drop the voltage from the 3.6 or whatever it charges up to, down to a lower level and give roughly, it's not super accurate, but it's a roughly 3.3-ish volt supply. So that's the power supply covered. It's quite a complex little circuit. Some nice features in it. So I'll brighten this image up. Will I regret brightening up? I don't really think so. So this chip here has the function of monitoring, and because it's monitoring, it uses, for the voltage, it uses this resistive dropper. Let me zoom out just a little tiny tad here so you can see the whole lot. It uses these resistors in series. They're not actually dissipating much power, but they've chosen them purely for their voltage rating and put loads of them in series, but they're also acting as links. Interesting that that one is actually hopscotching over a track that is effectively connected to neutral live, actually. This pad here is effectively live. This is the base reference for the whole circuit. That's the 0 volts that goes up through here to the Zener and up to the middle pin of the 78L05. That is basically, I'll just write on it, 0 volts. Because that's what it is to the circuitry. You'd still get a wallop off if you touched it. And that's why these capacitors are all coming down to that. They're decoupling capacitors for stability of the supply as it measures it. So in the case of the measuring the voltage, it's going through these resistors. It's forming a potential divider with this one, little capacitor to decouple it, and I'll show you this afterwards, and then it goes to the chip, and that's how it measures the voltage. For the mini avalanche in the vicinity. For the measuring the current, it measures the voltage across this big wire link here. That big chunky wire link here. And it is quite a beefy link. So the voltage across it, particularly at things like just a few milliamps, that's going to be super low. I can't believe how sensitive it is, but that is ultimately because this chip here is quite special. We'll tell you what, let's take a look at that chip. The inputs, and I'll show you what they are. So here's the circuitry it's using to measure the voltage. It's got that chain of resistors here, that's them. It's got this resistor here, that's that one, 360 ohm. And then it's got that little capacitor across it. But then it's also got this little resistor, 360 ohm, and a capacitor to the local 0 volt rail, which is effectively here, and it just compares the two of them. That's how it gets it boosts it up and then converts it to a digital figure through prescalers. It's really complex. The load sensing is slightly different. It's basically got an op-amp type device, and it has the resistor tapped off either side of that big huge current shunt, and that then has the coupling via the capacitors to the 0 volt rail. And the circuitry, the actual schematic, the information that came with this thing for the voltage, it gave two options. This is used in meters. This chip is used in professional applications. It has what they call a potential transformer, which is just a transformer that goes from, say, 120 or 240 down to a lower voltage. And that means that whatever the voltage is in the mains, it couples without any direct electrical connection via this transformer. So that circuitry can literally be at ground potential. But that's not being used in this instance. Because it's using the direct connection, it's got this potential divider that can be fine-tuned to this potentiometer. But instead of that, they've used that chain of resistors and a fixed resistor down here, and then they're just using calibration to adjust for that. So that is effectively the circuitry they're using here. The current sense there is showing the resistive shunt reference with the live, and they're showing that Earth symbol. That's misleading because it's not Earth. It's the referring to the sort of like the local ground. But they're showing the couple of resistors coming off that and the capacitors going to the ground. There is one other capacitor they've added for extra stability across those pins. This one here is different. And that equates to, on the drawing, that equates to that little sneaky extra capacitor there. It's interesting. Other components on this board are a local decoupling capacitor for, so this is getting its 5 volts, it creates a 1.188 volt reference, and that little decoupling capacitor there is for that. This one is for the 5 volt supply that's going into it, and this one that's not populated with a capacitor could, or maybe should have one for the 3.3 volt. I guess they just thought it wasn't needed. I don't know if that is being used. I should think it is probably being used for the internal circuitry. So I wonder why they've left that off. But they have. It's interesting stuff. So now we've ascertained that the power is being monitored by a dedicated chip that communicates via these 2 lines here that snake across and then go onto this connector. That goes up to the display chip. So we've got the microcontroller here. We've got the LCD display driver. That's why all the leads were going straight out. It is the microcontroller is a, let me just sort paperwork out here. It's an unusual one. It's a SIN 1 microcontroller based on 8051 architecture, which is a really old microprocessor technology from the past, but because it's got huge libraries of information, it's got a very popular and fairly well designed language. It's still popular. It's very current. So this basically lists all the sort of features. It's a Chinese data sheet, but it's a competent little chip. This chip here basically has everything needed for controlling the LCD. It's also got a tone output generator for a buzzer that's not used, LCD driver and bias and control and timing and communication. So it just basically takes the information from this chip and displays it to the LCD. The other components in the vicinity, that strange unregulated 3.3 volts that comes up here, comes up in these 2 pins and goes to this little decoupling capacitor locally for stability. The only other components on the board are these button pads, the zebra strip connection pads to LCD, and this 10k resistor, 1, 0, 3, 1, 0 and 3 zeros, and this little capacitor here, and that's the reset capacitor for this chip. So when you initially power this up from scratch, when there's nothing there, in the time it takes this capacitor to charge from 0 up to the full voltage, that will reset this chip. And when you press that little reset button in the front, you have to insert a tool to press it. Keep in mind, don't use anything too sharp because that is live behind that little piece of rubber. All that does is it shorts out that capacitor and resets the chip. So it's a very, it's a very straightforward thing. It's extremely surprising that it's got such a high profile chip in such a cheap device. I guess it's just the scale of mass production. But there we go. I have to say that I'm pretty impressed by that power monitoring plug. I thought the circuitry looked quite well designed. It looked quite professional. And just that little chip alone makes it kind of special because that does all the hard work. And it means that even with modern complex waveforms like LED lamps, this little chip can actually decipher those complex voltage to current ratios and give the power factor and give an actual real power indication. And I'm guessing that the calibration of this unit is done by the microprocessor, perhaps being put into that initialization mode, I'm not really sure, and then a specific voltage being applied to the unit and a specific load of a certain amount of current. And perhaps the processor looks at those, sees what it's getting, knows that they're roughly in the ballpark, and then it will send calibration values and check again, just keep nudging it until it gets its calibration value and then store it in the processor's own memory so that every time it powers up this unit, this chip gets the fresh data. That'll be why it's monitoring for loss of power. It'll be that little transistor there that tells it the power is being turned off will do two things. It will know when its power is applied again to go and rewrite the values into this, the calibration values. But it'll also know that when it detects the power going off, not to do anything that could involve saving to the microcontroller's memory if the power's about to go down. Though, having said that, it's got the battery back up on that. So it must be purely just to initialize that, and also so it can turn the display off when it's not needed, just to save power. But there we go. It's actually really well made. It's accurate, and it's quite well built, and it works well. That's another surprise from eBay.